webinar. So, welcome all of you for our today's webinar. Respected Principal Sir, Dr. Prasanna Kumar Dutta, distinguished guest, Professor Ghanshyam Bes from Northeastern Hill University, Shillong, and Professor Ramesh Chandra Deka, Dean of Sciences, Tezpur University, and also Professor of the Chemical Science Department, Tezpur University, my colleagues, and my dear student participants, friends from different colleges, universities, and institutions. I am Dr. Porinita Bora, HOD, Department of Chemistry, Bahona College, and host of the webinar. This webinar is organized by the Department of Chemistry, Bahona College. Before going to start this webinar, I'd like to request our principal sir to inaugurate this webinar and give the welcome address. Sir, please. Principal sir. Principal sir, please admit yourself.
Good morning, everybody. I, on behalf of the Bahona College family, Professor Department of Chemistry, NEHU, and Dr. Ramesh, Dean, School of Science, Tezpur University, to this webinar on chemical science. It is my pleasure to have these two eminent professors with us to interact with the students and faculty of chemistry. I also welcome teachers and students from different states and of our college to this webinar. Bahona College have been organizing seminars, workshops, and popular talks, and now webinar at different levels. Today's webinar come interaction is such a program organized by Chemistry Department of this college. I hope this webinar will help our students very much. The two topics selected are very much important, not only for the students of chemistry, but also for our other science subjects. Spectroscopic techniques are now widely used in practical classes undergraduate level. I hope that researchers with their vast knowledge make that clear to the students. In this context, I thank Dr. Porinita Bora, HOD Chemistry, for her effort in inviting the research and arranging this webinar. Once again, I thank Dr. Wes and Dr. Deka for your gracious presence in this webinar, sparing your much time. And with these few words, I would like to inaugurate this webinar of chemical science using its
Thank you, sir, for your inaugural speech. Now we are going to start today's discussion. First lecture will be delivered by Professor Ramesh Chandra Deka, and his topic is quantum chemistry. Before delivering his lecture, I introduce him with you. Professor Ramesh Chandra Deka did his PhD from Cotton College and MSc from Guwahati University, and he did his PhD from NCL Pune, National Chemical Laboratory Pune, and postdoctorate from Tokyo University in 2001. He joined the Tezpur University in the year 2001 as lecturer, and then he went to and did his again at University. Now he is the Dean of Sciences in the Tezpur University and the professor in the Department of Chemistry, Tezpur University. His research fields are interstellar modeling, quantum chemistry, catalysis, nanochemistry, and many more. Under his guidance, most students doing their PhD degree, he got many awards from India and abroad also. Now I request Professor Deka to deliver his speech, and I also request the participants' friends to note their queries in the chat box, and after of his speech, to interact with Professor Deka. Thank you, sir. Please start your speech. Sir, please, Deka sir.
Good morning, everyone. First of all, I thank just 1 minute. Dr. Boral, more degree of more the Sarah Koisu, Sarah. Oh, my visa of Koisu, and the more of degree of more on Belay on meeting on us. Sorry for the disturbance. So first of all, I thank Dr. Porinita Bora for inviting me to deliver a talk in this webinar. And I also thank the principal, Dr. P.K. Dutta of Bahona College, for giving me this opportunity. I'll be presenting, but I have not seen where is my presentation. So I have to share, no? Where is the sharing option?
You have to do present now, sir.
Yeah. Oh, yeah. Now I have seen. Yeah.
Yes.
Present now. Yes. So I'll be talking about quantum mechanics, quantum chemistry, which is very difficult for many of the students to understand. But what I will be doing, I will try to make as simple as possible and without much mathematics. Actually, what happens in quantum chemistry, we generally expect that there are a lot of mathematics, but it is not true. Actually, we deal with mathematics, which we study in higher secondary: addition, subtraction, multiplication, division, and maximum we need to go to differentiation and integration. So this is all about. We don't need more than that. If we know addition, subtraction, division, multiplication, and the differentiation and integration. So this is more than enough to understand quantum mechanics. Did you see my presentation? I have not seen. I put share presentation, then you are presenting to everyone. That also I click. So, but somehow it is not coming. You are presenting. Then we have two options only: stop presenting and you will presenting to everyone. Stop presenting is highlighted. Is it coming?
No,
Not
sir.
yet, no.
Sir, you have to open your PPT.
Huh?
You have to open your PPT, sir. The PowerPoint presentation you have to open.
Oh, sorry. I think
We can see your screen. Yes, sir. Now it is coming.
Now you can see, no?
Yes, sir.
Let me see whether I can see or not. No, I am not able to see. I am not seeing this presentation. But anyway, I can, if you can see, I can present. There is no problem. So what is there? Did you see the definition of atomic orbitals and molecular orbitals?
Yes, sir. Yes, sir.
Yeah, okay. Yeah. So what I will do, when I take first class in MSc or whatever level I teach, I ask, how do you define atomic orbitals? And many students, almost all, tells that this is the probability of finding electron around the nucleus of an atom. So, and this view is there for all of the students. So today we'll see how our textbook have defined the molecular orbitals and atomic orbitals. So before going to this definition, that when we wanted to study, say I wanted to do PhD in molecular modeling, many of the teachers told me, no, you don't do, because this is not chemistry. It is a lot of mathematics are involved. It will be very difficult. But then we'll see a little bit. So first I am defined. So it is coming in the textbook definition of orbitals. So the wave function psi wave function psi for electron in an atom and molecule, in atoms and molecule, is called atomic orbital. This is physical chemistry. Generally, we follow this Nagian and Then we also follow R.K. Prasad book for in quantum chemistry. For hydrogen-like in the inside bracket, that is one electron atom. The wave functions are also called atomic orbitals. Means hydrogen-like atoms or hydrogen-like one electron wave function is called atomic orbital. And then B.K. Sensor, so who was our teacher, his book defined one electron wave functions are called atomic orbitals. Then nowadays many people follow this book, Quantum Molecular Quantum Mechanics by Atkins and Friedman. So one electron wave function in atoms are called atomic orbitals. Then Levine is defined a one electron wave function is called an orbital. So whatever our student used to tell, the probability of finding electron, none of the book has told that atomic orbital is the probability of finding electron. So why this book? All the books have defined that a one electron wave function is an atomic orbital. So in today's lecture, I will try to make you understand this statement that one electron wave function is an orbital. So this equation everyone knows, because this equation they are even in higher secondary book. H I is equal to E psi, where H is the Hamiltonian operator and psi is the wave function and E is the energy. So are you able to follow my slides? This is the slide number 3.
Sir, please do slideshow.
Oh, slideshow. No. Okay.
If it is possible.
So which slide you are seeing?
Yeah, this one.
Slide number 2.
Yes, sir. We can see.
Slide number 2 you are seeing?
Yes, slide number 2 we are seeing.
Okay. Then this is slide number 1, then 2.
Yes, sir. Yes, sir.
So we have the definitions. Okay. And then now slide number 3 you have seen.
Yes, sir.
Is it fine?
Yeah. Yes, sir. I'm fine.
Okay. So what will tell why it is important? This H psi is equal to E psi. Although for many chemists it is not familiar. So you know, in 2013, 3 persons got Nobel Prize in chemistry: Martin Karplus, Michael Levitt, and Arya Warcel. If you see recently, Michael Levitt is very active in COVID-19. He has many lectures, YouTube video lectures, and also many manuscripts he has written on COVID-19. Very interesting lectures. So you can follow those lectures. Whether people are doing right or wrong, you can find out from his lectures. And this tea, the Martin Karplus, he was born in Austria, which is in Vienna, which is capital of Austria. And then due to in 1930 he was born. In 1933 Hitler took over Germany, and then there was a lot of problem towards the Jewish people. And Martin Karplus being a Jewish, so his family was forced to leave Austria, and they went to France. After spending few months in France, they went to America. Then Michael Levitt is also another Jewish. He was born in South Africa, but to a Jewish family. Arya Warcel was born in Israel itself. So these 3 gentlemen got Nobel Prize for developing one computational technique to take care of large molecule, very large molecule. So these slides I am presenting to show when these 3 gentlemen got Nobel Prize. So there was very big headlines in Israel. And then one heading is called Tiny Israel is a Nobel heavyweight, especially in chemistry. So then latest Israeli laureates, Arya Warcel and Michael Levitt, are the 5th and the 6 winners of the chemistry prize under a decade in less than 10 years. So 6 person got Nobel Prize in chemistry from Israel. Then another heading is 3 Jewish professors, 2 of them Israeli, shared 2013 Nobel Prize in chemistry. So why I am showing this one? Say in 1 decade, 23 person got Jewish person got Nobel Prize. Say from 2003 to 2013, in 10 years, 23 person got Nobel Prize. Jewish professor got Nobel Prize. And if we see the entire list of Nobel laureates, then we will find that about 22% Nobel laureates are Jews. So I am showing these slides. The Israel that area is about 20,000 kilometer square, and population is about 8 million. So Israel, it is, and Assam, I am comparing Assam. So Assam is about 4 times bigger than Israel, and population is also about 4 times. So, and we generally complain that we have a lot of troubles, insurgency problem, but I think Israel having much more trouble than we have. So that cannot be excused for doing science or anything which can give international recognition. So I'll skip this introduction part of marketing purpose. I have already told. And then area or cell. So these are all informations are available in website. And what these people did, this is the molecule of retinal, so which is responsible for our vision, for this molecule. No? So in this molecule, there are cis-trans conformation. So one, when the compound is having cis conformation, we are able to see. If it is trans conformation, then we cannot see. So this molecule will not show any fission. So people wanted to understand why this type, how this is responsible. But these big molecules in 1976, it was impossible to study, to do any theoretical calculation in these molecules. But these three gentlemen developed the theory how to take care of. The quantum mechanics, we can handle very small molecule. And there is another technique called molecular mechanics where we can handle very big molecules. So, and these 3 gentlemen developed theory to combine quantum mechanics with molecular mechanics, which is popularly known as QMMM method. So then this figure, so you can see there is one person, this is G.N. Ramasandran. Then this is Linus Pauling, and this is Dorothy Hopkins. Dorothy Hopkins also visited Assam in 1979, and in fact she inaugurated that institute, which is known as IASSST. So she inaugurated in November 1979. So this G.N. Ramasandran, he was a professor at the University of Madras, and he developed one model for understanding very big structure of protein. And if you open any book on protein structure or any book on biochemistry, you will find something like called Ramasandran plot. So he published several papers in 1954, 1955, and you can, this Ramasandran plot is very important to understand the structure of protein. But his calculation was based on MM, which I call molecular mechanics. So I am showing another gentleman from India. So he is Anizur Rahman. And you know that Newtonian mechanics, Newton's law of motion, this particularly second law of motion, F is equal to ma, is applicable only to very large systems like cricket ball, football, planets.
Hello.
Hello?
Sir?
Yeah.
Sorry to interrupt, sir. Sir, can you start presenting again? I mean, continue presenting again. Someone actually interrupted. That's why people are not seeing the slides.
Oh, so I have to stop sharing, no?
No, you can. I mean, sir, start sharing and continue from this slide.
Okay.
There might be
Is it
something
okay
called
now?
resume presenting.
Yes, sir. You can resume because of okay.
No, can you see Professor Anizur Rahman in this slide? Hello?
Yes,
Yes,
sir.
Yes, I can see. Okay.
It's working, sir. You can continue.
Sir, you continue.
It is working now?
Yes, sir. You can continue.
Yeah,
sir.
yeah. So this is Professor Anizur Rahman, and he developed one theory. Generally, Newton's law of motion, this F is equal to ma, is applicable to very large systems, planets. So we used to study about movement of train, bus, and in higher secondary we solved many problems using that equation. But Professor Anizur Rahman, he used this F is equal to ma for small system, for molecules. So he is the first person to develop the molecular dynamics. So dynamics is there. If we use Newton's equation, it is called dynamics. But molecular dynamics, this term, was used by Professor Anizur Rahman, and he is the first person to do molecular dynamics. And we should be proud that the Indian initiated this field. Nowadays, this field is very attractive in drug design or in studying structure of protein, DNA, even other big materials. And then now I'll come back to our topics with little bit introduction. Then Newton's equation F is equal to ma. So we solve for very large system. And Schrodinger equation H psi is equal to E psi is applicable to very small system. And we know from our textbook that we can solve this equation exactly only for hydrogen-like species, hydrogen atom. So these three gentlemen, as I showed in the slide number 3, they combine these techniques, Newton equation, F is equal, this is ma, molecular mechanics, with QM, the Schrodinger equation. And earlier, the Newton's mechanics and Schrodinger equations were rival to each other. But in 2013, or in fact, in 1976, that equation was developed for good collaboration between Newtonian mechanics and Schrodinger cat. So not only these three gentlemen got Nobel Prize in chemistry for developing quantum mechanics, there were other people, Martin, these three gentlemen got in 2013. And then in 1998, Porter Kohn and John Anthony Popol got Nobel Prize in chemistry for developing theoretical methods. One is called density functional theory. And then in 1991, Kenichi Fukui from Japan, and then Ronald Hoffman. These two gentlemen got Nobel Prize for developing one theory called frontier molecular orbital, FMO in short. Then Robert Mulliken also got Nobel Prize in chemistry for theoretical work. Then we have Linus Pauling, who got Nobel Prize 2 times. One for chemistry, the other one for peace. And he's supposed to get Nobel Prize 3rd time for DNA helix, but somehow he missed. And that went to Watson and Crick. And then I will start a little bit about the failure of classical mechanics. So we have only 4 theory which the classical mechanics could not explain. One is black body radiation, that is there in our textbook. Then second one is photoelectric effect. Third one is heat capacity of solid. And the last one is the line spectra of atoms. So towards the end of say 19th century, the physicists thought that all the theory have been developed. So there is nothing new to be developed, except whatever theory have been developed, we have to manipulate to understand these 4 phenomena. So they thought that everything is done. So black body radiation, when with the existing theory, Rennie and Jean, these 2 persons, Rennie and Jean, they use the theory of whatever is there towards the end of 19th century, and they got one equation. If we plot that equation, the plot is like this line, that green line. And experimental black body radiation is like this, the pink line. So this is the experimental one, black body radiation. So when we plot the Rennie's equation, so we get a similar pattern up to some temperature or up to some wavelength, and then it never came down. So it goes up and up and up. So this is called ultraviolet catastrophe. So this, because in ultraviolet region, when we go towards ultraviolet light, so we could not, people could not reproduce the experimental finding. Similarly, photoelectric effect, I will not explain much about this photoelectric effect. They generally, classical mechanics thought that if we increase the intensity, so your the energy will increase, but this is not the case. So we have to increase the frequency. You can read those things in details. And then this is heat capacity of solid. So in 1819, Dulong and Petit proposed that the heat capacity of solid is constant. So it is about 25 joule per Kelvin per mole. But again, if you do experiment at low temperature, the heat capacity, molar heat capacity decreases, and it reaches 0 as temperature tends to 0. So at T is equal to 0, it should be 0. But at high temperature, it is constant. So it will be constant like this. So these phenomena, people could not understand why this is happening. Then the atomic spectra, you know this series, Bahona series, which is here, this in a visible region. So Bahona was a school teacher. So he found this series of spectra, and because of that, it is given his name. And he also gave one equation in 1885 to explain this spectra. But there was no theory to explain this spectra. Theoretically, we could not, a basic theory was missing. So then many people tried to develop this theory, and then I think I have not put Planck theory, Planck distribution law. So in 1900, December 14, Max Planck gave a presentation among the scientists in Berlin, and he tried to explain the black body radiation by developing one equation. And if we plot that equation, the behavior is like this. So it will, as we increase the wavelength, radiation will increase, and then it will reach maximum, and then it will come down. So he started, but many people criticized and even laughed at him, his theory. But then in 1905, Einstein used his equation. E is equal
Pardon,
to
sir?
Pardon?
Pardon, sir.
Yeah.
Sir, students are saying they are not being able to see the slides. Sir, could you please,
What
I
to
mean,
do?
yeah, you can stop sharing first.
Yeah.
Then again you start sharing and resume the slides.
Oh, okay.
Yes.
Okay, just 1 minute. Is it okay now?
Sir, you have to start presenting.
Or that also I have to do, no?
Yes, sir.
So slideshow I have to do it, no?
Yes, start presenting, then slideshow you can do.
Start presenting I might have done. Oh, no, I have not done. So I think I have done now.
Yes, sir.
Then I have to show the presentation.
Yes, sir. You can start the presentation and resume from wherever it is.
Is it okay?
Yes, sir. So it is
it okay, Sampath?
Yes, sir. Yes, it is. So you can continue, sir.
Yeah,
Sorry.
okay, fine. Yeah, no problem. So in Max Planck, whatever Max Planck gave the equation E is equal to h nu, and Einstein used this equation and then explain the photoelectric effect, and they could also explain the black body radiation by using that equation. And then there are a lot of development. The Compton effect also you explained by using this equation. Then people started believing that something is correct. Whatever Max Planck told in 1900 is correct. And then J.J. Thomson told that these electrons are having particle-like behavior. But then his son again, Thomson, he told that it has also behavior of wave-like. Then we have De Broglie, who developed the wave-particle duality. So in the meantime, Schrödinger, he is also an Austrian mathematician. So he started using wave mechanics, wave equation for electron. And since electrons are also having wave kind of behavior, so he tried to develop this behavior of the electrons by using wave mechanics, and then he derived the equation H psi is equal to E psi, which is known as Schrödinger equation. So in this equation, H is Hamiltonian, and psi is wave function, and E is the energy, and psi, we get the same psi in this equation. These are called eigenvalue equation. So, and this Hamiltonian represents the energy. So it is not very difficult. So psi wave function, and we have some postulates in quantum mechanics, which will tell. In the later slide, I will explain these things. And psi, generally when we ask students, so they tell that orbital is the probability of finding electron. But we will understand in today's lecture that psi is the orbital. Psi is the orbital. So, and we will understand the psi is the one electron wave functions, which we started in the beginning. And when we square it, and multiplied by the volume element, we get the probability. So when we ask what is the orbital, student used to tell that probability of finding electron around the nucleus, but this is not. This is the, your student used to tell the square of the wave function, orbital. Size the orbital, that we will understand towards the end. And this is one interpretation called Born interpretation. So if we integrate the total, if we find out the total probability of the electrons around the volume element data, so it comes to unity. So this is called Born interpretation in our textbook. And because of that, our wave function should be normalized. And then little bit about this Hamiltonian. So this is simply the kinetic energy and potential energy. So kinetic energy, it is half mv square. This kinetic energy in classical mechanics, it is half mv square for one electron. And this is the potential energy. So if we have two charged particles, the Q1, Q2 divided by 4 pi epsilon r. This kinetic energy T, if we express in quantum mechanics, it becomes like this. H squared square minus H squared square divided by twice ME plus Laplacian square. So this is not very difficult, simple differentiation. So we can convert kinetic energy half mv square to, this half is already there. But if we simplify, there is something called atomic unit. So in atomic unit, H cut is equal to 1. So and ME is equal to 1. It will be simply minus 1 by 2 Laplacian square in atomic unit. And in this place, in atomic unit, E is equal to 1. 4 pi epsilon is equal to 1, so it will be simply 1 by r. So for hydrogen atom, it is very easy to remember. This Hamiltonian operator for hydrogen atom will be minus 1 by 2 Laplacian square and minus 1 by r. And so if we expand this Laplacian, so we get this x, y, z in terms of x, y, z coordinate. So we get this equation. So which look little bit complicated, and it is much more complicated to solve in Cartesian coordinate. If we use Cartesian coordinate, it is impossible to solve Schrödinger equation even for hydrogen atom. So because of that, in our quantum chemistry book, we have one chapter on hydrogen atom. So first we transform this Cartesian coordinate. XYZ is called Cartesian coordinate, XYZ coordinate. So we have to transform this one to spherical polar coordinate, which look much more complicated. The expression is much more complicated, but by transforming this equation to that complicated equation, we can at least solve the equation. Here it looks simple, but it is impossible to solve. So maybe if someone asks me a question, then I will explain why it is impossible to solve. So for the time being, you just remember that at Cartesian coordinate, at XYZ coordinate, we cannot solve the Schrödinger equation even for hydrogen atom, one electron system. So we have to convert this one to spherical polar coordinate. So this is at this part I have already explained, and then I told about all the history of how many Nobel Prize was there for quantum chemistry, but there are many more in physics. So I have shown some figures here, and I also made a list 1, 2, 3, 4, 5, 6 up to 25. So 25 persons got Nobel Prize in physics. I think there is not a single field where so many Nobel Prize was awarded. So all those people got Nobel Prize by giving their by spending a lot of time in H psi is equal to E psi in one equation. So why in chemistry we are spending so much time and making our students' life miserable by teaching quantum mechanics? So we have to understand the first postulate. The first postulate of quantum mechanics. So this we have to understand. So what it is telling, I am reading this one, then I will explain. Every physically reliable state of the system is described in quantum mechanics by a state function psi that contains all accessible physical information about the system in that state. So in books it will be written, the summary of the statement will be something like that only. But when I was student, I did not understand this. What is the meaning of this? We remember these things, everything we remember and wrote in exam. So now I'll tell in my language. So what it is telling, so every system means every atom or molecule in our quantum, in our chemistry, whether it is organic molecule or inorganic complexes or in our gas phase molecule, any molecule can be expressed by a function called psi. And this is a function of x, y, z coordinate and time. So this psi is a function of only x, y, z coordinate and time. So if we don't take into account the time, then we can simply write that psi is a function of x, y, z coordinate. So which is simple, like we generally write f x, y, z, but here we are writing psi x, y, z. So every system, every molecule or every atom in our chemistry can be expressed by a function called psi. And later part it is telling that this psi contains all the information about the system. So generally when we go to buy a mobile, we take what are the functions. Whether say earlier nowadays there are a lot of functions. Earlier we used to go and see whether there is camera, whether torchlight is there or not. So we used to see multiple functions. So if we have more functions, we buy that mobile. But what is psi function? Is this psi function? So every system, every molecule can be represented by this function psi, and psi contains all the information about the system. Not only that camera, mobile, whatever information we have, it is not like that. It contains all the information about the system. So all information in chemistry means what? What information we need as a chemist? So we need energy. Then we need the dipole moment of the molecule, or polarizability of the molecule, or charges of each atom in the molecule. Then Fukui function. So many properties. And then we need vibrational frequency of the molecule, functional group present in the molecule, or NMR chemical shifts. Whatever information you need, everything is there in this psi. So because of that, we all are studying this psi. And in chemistry, say if we want to determine the structure of water molecule or any molecule, we need to have one X-ray machine. But the one X-ray machine costs about 3 crore. And even in our Tezpur University, for many years, we did not have X-ray. Only recently, we got X-ray machine to study structure of molecules. But if wave function, if we know the function of the molecule, psi of the molecule, then we can get the structure of the molecule. And we need not spend much money, because we have to have a computer, small computer, like PC, which cost about 30,000 rupees. So instead of spending 3 crore, we can spend 30,000 rupees. And there are many software which are free. So we can freely solve the psi for many molecules. So because of that, people are spending time in understanding psi. And chemists, and it is important for chemists, because even if we don't have, and also you see, for X structure, we need one X-ray machine of 3 crore. Then for if we want to calculate and determine NMR chemical shape, we need another 5 crore to buy one NMR machine. Then if we want to get the IR spectra of the molecule, we need to spend about 32 lakhs to buy one IR machine. But all the information is there inside. By spending 30,000 rupees, I can determine the structure of the molecule. I can get the vibrational frequency of the functional group of the molecule. I can get the chemical shift, and for a proton NMR shift, I can get carbon NMR shift. And for if we buy one NMR machine for hydrogen, there is different probe. For carbon, there are different probe. For silicon, for aluminum, for chlorine, for everything we have different probe. But psi contains all information. So all in one. It is not 2 in 1 or 3 in 1. Psi is all in one. So because of that, we in chemistry we study psi, Schrodinger equation, and we study quantum chemistry. And quantum chemistry is very essential for chemists. So then, as I told earlier, the square of the wave function psi square is the probability density for finding the particle at that location. Psi square is the probability density. So when you are asked what is an orbital, if you tell it is probability of finding electron, so that will give, you are telling psi square d tau. If you remove d tau, psi square is called probability density. And psi is the wave function, and psi is called atomic orbital. So there are these things you write, you read in a book, say single value of continuous fast derivative, quadratically integratable. These are the definition of, say, the psi should satisfy this condition. And then psi square is the probability, this I have already discussed. And then, so I told you in the beginning that half mv square we have to convert to quantum mechanical operator. This is the way how we can convert that classical mechanical momentum to quantum mechanical operator. So operator comes in your third postulate. Second postulate comes the operator. So whatever we want to observe, say we want to calculate energy of the system. We need one operator for energy. If we want to calculate vibrational frequency, we need one operator corresponding to vibrational frequency. If we want to calculate NMR chemical shift, we need to have one operator. So for each and every observable, there is a quantum mechanical operator. So we need to have a quantum mechanical operator. Then third postulate tells about it should be eigenvalue equation. So each psi is equal to E psi. Then fourth postulate give you the expectation value, and fifth postulate will tell you the time dependent Schrodinger equation. So we did not know those things. So I am telling this is wrong. Because in a free particle we don't have -1 by r. So this is the operator for hydrogen atom, not for free particle. For free particle it will be -1 by 2 Laplacian square. Simply -1 by 2 Laplacian square. And this is for hydrogen atom. Then we can have all systems in So I told that if we write the Schrodinger equation, this Laplacian, in terms of Cartesian coordinate x, y, z, we cannot solve. This is impossible to solve the Schrodinger equation exactly, even for hydrogen atom. So we have to convert to spherical polar coordinate, where which means we have to express x, y, z expression in terms of r, theta, phi. So these three equations you should note down. We will need later on. We need this equation later on. But I have to also quickly go because it is already 11:50. And then I am telling for the student to note down these three equations. X is equal to r sine theta cos phi. Y is equal to r sine theta sine phi. And z is equal to r cos theta. So how we transform this x, y, z to spherical polar coordinate?
Sir, we cannot hear you, sir. Hello, sir.
I think your microphone is off. Please, please switch on your microphone. Professor Deka, please switch on your microphone.
Yes. So now it is okay?
Yes, we can hear you.
Oh, okay, you are back. Okay. So, so recently you are not hearing for a long time or now only?
Now only, now
Okay,
Maybe
fine.
10 minutes I'm here.
I don't know how it happens. And then you see, so this this simple equation we need to convert to a very complicated equation. Otherwise, we cannot solve Schrodinger equation. It is impossible to solve. So then we have a very big chapter in our quantum mechanics, about 10, 15 pages. Then after a lot of manipulation, we solve this equation. Then we get this L, ML, then N values, so that quantum number comes. So I am not spending time on this. So this came from the derivation of, lot of derivation, about 10 pages in our quantum chemistry book. After converting that Cartesian coordinate equation, H psi is equal to E psi to spherical polar coordinate, we are solving the equation. So I hope students have noted down these three equations because I need. So now I am coming, and after this equation, we get one expression for psi. That expression I have. So we get the expression for psi. So the wave function for an electron. So there for an electron in an atom is called an atomic orbital, described by three quantum numbers N, L, ML. So we will have a very complicated expression after solving the Schrodinger equation for psi, and that complicated expression, why we call, say in higher secondary we studied f is equal to e to the power minus x is a function. So if we write something is equal to e to the power minus x, that become a function. So here if we write psi is equal to e to the power minus x, y, z, something like that, so then we will call a function. So that function is called atomic orbital. So psi. If we square it, we call it probability density. If we multiply the square by d tau, it is called probability. So when you define atomic orbital is the probability of finding electron, you are telling this equation. You are not defining psi. So in order to define psi, you have to tell that an orbital and one electron wave function, or the the expression which we got from by solving Schrodinger equation psi is called an orbital. So now I am giving this expression. Now, if I ask some questions, so what is this orbital? So I will get psi is equal to psi is equal to this expression. So I will get this equation. So this may be complicated, but not complicated. If you remember that equation, so I will put it. So what is this equation? Psi. This is said if you are in those who are in 6th semester, or they might be in 5th semester. I don't know in which semester students are. So this psi, if we write this equation, so in this equation there is no theta, no phi. So it will be S orbital. Now which S, whether it is 1s or 2s or 3s. So it will be 2s. So that also we can find out, because in this equation, when z by r, zr by a becomes 2, so this equation will be 0. So 0 means there will be one node. So in s orbital, only 2s orbital we have one node. So because of that, it will be 2s orbital. Because our psi 2, 0, 0, this expression will be psi 2, 0, 0. So is like this, and we will get the function. So this equation we have theta. So theta means it cannot be s orbital. So it will be p or d orbitals. But then so there is no node in this equation. So, and also it is simple. Say those students who have noted down, the x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So here you see we have r and cos theta. R I think I'll not make you life miserable. These also you can simply find out. Say if we expand cos twice phi, like cos a plus b is a formula, then we will be able to find out whether it is 3d z square or 3d x square minus y square. It is not 3d z square. It cannot be 3d z square. 3d z square will have only r square cos square theta. If there are r square cos square theta, it will be simply 3d z square. So it may be this equation can be either 3d x square minus y square or 3d xy.
Hello.
That we have, hello.
Okay.
So this is simply 1s orbital, because we don't have any node. So like that we can find out. So I will not. I think students are very small now in this at this level. So I used to make. I used to present this one in many colleges, and then after ending my lecture, I used to take this exam, maths the following. Yeah, so today I will not elaborate. I have told briefly how to identify the orbital, and all the orbitals is being a function, and this function comes from the solution of Schrodinger equation H psi is equal to E psi. When you call 1s is an orbital, say this is 1s is an orbital, but this orbital, this 1s is equal to this equation J. So this is the expression for 1s. So you are telling 1s is an orbital, but when you are asked to define orbital, you tell the probability of finding. So that is the mistake you used to do. So what we have understand, 1s is equal to this function, and this came from the solution of one electron wave function for hydrogen. So because of that, we define an orbital. as a one electron wave function. So I think I have finished, and this is more for many electron system I am not going to discuss. So I think I tried to explain the term orbital. So once we know those orbital, we can use that system to many systems. So any large system we can use. So I think this is all about what I wanted to talk today. And thank you very much to everyone for your attention. And if you have any questions, you can ask me.
Thank you, Professor Deka, for your valuable lecture. There are many questions I see in the chat box put by our student participants. So now I request our assistant coordinator, Dr. Sampok Doctor, to conduct the questionnaire session, and Professor Deka will answer the question to our students. Please, Sampok Doctor, carry on.
Thank you, ma'am. Now I'll start the questionnaire session. Professor Deka will take a couple of questions from the students as well as all the participants. So I would like to request the participants to put their questions in the chat box. Thank you. Please put your question in the chat box. If you have any question, then you can put in the chat box. Professor Deka will answer for you.
I think they may directly ask you also. That is no problem.
Yes, that is also all right. You can ask directly.
No question.
Sir, you can stop presenting now.
Oh, yeah.
So we have enjoyed a lot your presentation. I think we don't have any question for you now. Now I'd like to request our head of the department, Dr. Pointa Bora, to continue the forum with the next speaker. Thank you very much, sir. Ma'am. Ma'am, we cannot hear you. Ma'am, you are not audible. You have to put on your...
Thank you, Dr. Sampok Doctor. I again thank Professor Deka.
But there are some questions, I think. Why
Ma'am, hang on a second. There are some questions.
There are some questions.
Yeah, there are some questions, sir.
Yeah, I could not see you. You can read it if you.
Yes, sir, I can read it for you. So, Iftikhar Hussain is asking, what is radial and angular wave functions? In simpler words, what is
say in that equation? So this is that psi. For some equation, the psi does not include theta and phi. If theta and phi are not there, so it is radial function. So it independent of angular part. So if the function is dependent on phi and psi, so we call it angular. So like p and d orbitals will be angular. And then as all orbitals, we have independent. There is no angular part, and there are radial. So I think that question would have been, what is radial distribution function kind of thing? If p orbitals also we can plot as radial distribution function. So that they are in our textbook. So that equation means how this function varies as we move from the center of the nucleus. So that variation we can find out by radial distribution plot, where we plot psi square, not psi. Psi also we can plot. In fact, in our student, I used to teach our students, they plot the orbitals in Excel. In Microsoft Excel, they can write the function, and by varying R, they can write the, they can find out the value of psi, and then they plot how it looks.
So we have the next question asked by Asim Tamali about why Quadrangle equation becomes impossible to solve for many electron systems.
Okay. So so that in the presentation it was there.
Yes, sir.
Even for helium, helium is a mini electron system for us. No, we need not go for a big system. So when we write the Hamiltonian for helium, so we will have one term called 1 by R12. Say electron-electron repulsion is there. So this, the electron-electron repulsion is there. Due to this repulsive term, what happens? We cannot write helium as 2 hydrogen atoms. So if we could have written this Hamiltonian for helium as sum of 2 hydrogen atoms, that would have solved our entire problem. But it is not like that. Due to the presence of 1 by R12 term, we cannot write the Hamiltonian for helium atom as a sum of 2 hydrogen atoms. So in the language of quantum mechanics, I have to tell that the Hamiltonian is not separable. So we cannot separate the Hamiltonian for each electron due to the presence of electron-electron repulsion term. So that is the reason why we are not able to solve Schrodinger equation for mini electron system.
There is one more question which would be a little bit lengthier to answer. So I would ask first to you if you have time for answer this one also. So this question.
My meeting started at 11 o'clock. So better I leave. But I would have been happy to answer. If maybe one question I can answer.
So so this is asked by Pallavi Saikya. She is asking you to explain how the Schrodinger equation is used to solve 1s, 2s, 3p, 3d orbitals in the last slides.
Oh, so it's a first thing is the Schrodinger first step to write the when we write psi is a function of x, y, z, simply x, y, z coordinate. So first step is to write the Schrodinger equation in terms of spherical polar coordinate. After converting this to spherical polar coordinate, what happens? We will be able to separate the Hamiltonian first into 2 parts. One depends on R, the other depends on phi and psi. And then there are other mathematical manipulation where we will be able to separate phi and psi into 2 different equations. So finally, we will be able to write the h psi x, y, z is equal to psi r, means one part depends only on r. Psi theta, which will depend only on theta. The other part will be psi phi, which will depend only on phi. So psi x, y, z, where psi x, y, z, we cannot write psi x into psi y into psi z. We cannot write. But when we write psi in terms of r theta phi, we will be able to write the expression psi r, psi theta, psi phi. So as a product of 3 independent functions. So because of that, we can solve the Schrodinger equation by writing it into spherical polar coordinate. So in short, I can tell like that. But these mathematical details are there in any textbook. So, but this is the logic behind separating the psi into three product of 3 functions.
Thank you, sir. So because of time constraint, now I'd like to finish this questionnaire session. So I'd like to request Pointa ma'am to continue the forum. Thank you, sir.
I again thanks Professor Mesandebeka. In spite of busy schedule, you are encouraging our participants by delivering your valuable lecture. Thank you again, sir. Thank you, Sampok Doctor. You also.
Yeah. Okay, thank you. Okay, you please carry on.
Thank you. Now we are going to start our second discussion. The second discussion will be delivered by Professor Ghanashyam Des, and his topic is spectroscopy techniques in chemistry. Now, before going to his discussion, I am introducing him to you. Professor Des did his BSc from JD College and MSc from Guwahati. and he had done his PhD work at RRL in Jorhat and got PhD from Dibrugad University. He was working at Dibrugad University from 1999 to 2006, and then he went to Texas and Kansas for higher studies. Now he is the professor of the Department of Chemistry, Northeastern University, Ceylon. His research interested fields are asymmetric synthesis, green synthesis, and uh, solid state synthesis, etc. And under his guidance, many students doing PhD degree and completed PhD also, and he got many awards also. Now, I request Professor Bales to deliver his lecture. Please, Professor Bales, please carry on your lecture.
Yes, yes. Thank you, ma'am. First of all, I would like to welcome all of you to this lecture. And one thing we can do, I think, from admin side is that we can block the video for attendee, because that is kind of a distraction all the time. So whenever somebody wants to interact, they can interact by by the chat box. So that is better. So I would request all the participants to close their close their camera, okay, so that there is no other disturbance. Okay, so firstly, I would like to thank you, Porintava, for inviting me to give a lecture. Of course, she gave me a very difficult topic, analytical, studies in chemistry. So it is a pretty huge, huge subject area. So telling something within a short span of kind of 45 minutes to just 60 minutes, it is very difficult. But somehow I tried something and took just a simple example to tell you that how these analytical techniques can be employed to identify chemical compounds. So that is what I'm going to deliver it today. So I will go to enter. I don't know, I am finding an issue about a window. Okay. Why it is so? Let's get permission. What is this? Why there is no permission? I don't know. Let me see. Use this camera screen. Permission. Okay. See now. Okay. So I hope you people can hear me, right? Hello.
Yes, we can hear you. Yes, sir. Yes, sir, we can hear you.
Okay, okay, fine. So,
Now you can start slideshow, please.
yeah. You are presenting slide. Yeah. Okay. So let me go to this one again. There is an issue. Let's see. Let me go back again. Can you acknowledge?
Professor Bess, we cannot see you. Professor Bess, we cannot see you, neither we can hear you. Sorry, participants, we are having some technical issues with the speaker. Please have patience for some time. We can see you, Professor. You are not audible. Yes, we can see your presentation, sir.
Okay.
Yes, sir.
Hopefully now. Hopefully now you can see it everything, right?
Yes, sir. You can start presenting. Slideshow. You can start.
Okay. Okay. So thank you, everyone. Today I'm going to present about spectroscopic technique in chemistry. So as just I want to introduce myself. I'm from actually from Mazuli. So I'm working here for last 16 years in Department of Chemistry, NEHU, and I'm teaching organic chemistry. So here I'm going to talk about few spectroscopic technique, which is IR, NMR, and mass. How these techniques are used to identify a compound. That is the idea. So I hope everyone is hearing it, right? Hello.
Sir, we can hear you. Yes, sir.
Yeah. Okay.
Sir,
So
if you slideshow, then it will be better for us.
Yeah. Have you seen the slideshow now?
No, we can see the slides, but it is not a slideshow. It's not in the slideshow mode.
Is it? Why it is not? Okay. Let me put it again. Is it okay now? Hello.
Sir, you carry on, please, sir.
Is it okay now?
It is still not actually a sliding slideshow mode. Just slides we can see.
Is it? How come? And so, why is it so?
Yes, there you can click, sir, on current slide.
Yeah, that is what I'm doing. But it is not coming now.
No, not yet, sir.
But to me, it is showing that it is in slideshow mode. Okay. Somehow, maybe what I can do. Let me see.
So you may present anyway, sir. It is
No. That is not that will not be good. But to me, it is showing that it is in slideshow mode. Window share click control. Why it is so? Let's expand it. Maybe size of this file. View. Can I increase it? Okay, let me see. Somehow it is not going there. Yeah? It's not coming, right?
No, sir. Or you can
Okay.
try that, sir. Bottom one, sir. Bottom. There you can try the slideshow. Play slideshow bottom. You can use.
Bottom one also I tried. Not responding.
Toolbar at the bottom of the slide.
Yeah.
The fourth one by 100%.
Everything is low temporarily. Why it is not coming? I don't understand. Allow. No, so you can submit it custom slideshow. This. It is not coming, right?
No, sir.
But I'm in a meeting now, I'll call you. Can you see it now? No.
We can see the slides. You may carry on actually. If you...
This is going very bad. Why it is happening like this? I don't understand myself. But it is showing that it is in F5. Let me put F5. Now also you cannot see it like that only. Okay, let me start it like this only. Okay.
Yes, sir. We can. We'll be.
Yeah.
We'll be able to see anyway.
Yeah. So idea is that I'm going to talk about spectroscopic technique in chemistry. That means I will just use three equipments, that IR, NMR, and mass, to talk about how this compound can be purified and how this compound can be identified. Now, if you can see it out here, this is the simple sanitizer bottle. Now, idea is that, can you see I have removed the label. Now, can you say that it is a sanitizer bottle, or whatever content it is there, whether it constitutes the components of sanitizer or not? Now, if you see out here is that this sanitizer bottle is fine, but inside there may be hydrochloric acid. It may be sulfuric acid rather than ethanol or isopropanol. So what we'll have to do is that we'll have to see, we'll have to verify what kind of compound it is. So bottle seems like a simple sanitizer, but we cannot use it without verifying. So we should definitely look for, should we not look for ethanol or isopropyl alcohol out here? So that is the whole idea. Now, in your higher secondary level as well as BSc level, you have seen that you have done experiments that, okay, some salts are given, chemical salts are given, you are told to identify it. How do you do it? You do it by studying their physical properties as well as their chemical properties. So if that means if you are given any unknown thing, you must have to look for their physical as well as chemical properties if you want to identify them. So that means physical property means state, color, smell, solubility, melting point, etc., etc. A lot of other things, you can, different physical properties you can study. Similarly, chemical properties means you can use that compound, use that material to try with some acid, some base, or some other reagents to identify that what kind of constituents are present in the whatever compound you are getting in. So this is just, these are two examples. So even for inorganic compounds also, in your BSc practical, for sample analysis, you used to get it similar physical and chemical properties, where you used to study those things. Then what you do for chemical properties, initially you separate the mixtures, then you identify the elements, nitrogen, sulfur, halogens, then you study the functional groups, then you just prepare the derivatives of them, and then compare the melting points, okay, to identify that whether this is the compound or not. Suppose you have simple ethanol, then you will make, suppose, ethyl ester derivative, and then you will see the melting point which ethyl is heated, whether your prepared derivative as well as ethyl is heated has the same melting point or not. But there is another tool which can be very conveniently used it, and nowadays most of the labs, MSc labs at least, they use it. That is what is called spectroscopic analysis. So there are many spectroscopic analysis actually, but in this lecture I will just, as I have told you, I'll include only three, that is IR, NMR, and mass, to identify that what kind of constituent is there in this bottle. That means to identify whether ethanol or isopropanol is there or not, at least that I will identify out here. How to do it? Now I will take first this kind of IR spectra, okay? IR spectra, because I am not going to talk about theory to you out here, is because all the time you are getting theories, but getting a crude spectra and how to analyze them, that is my idea. Now if you see this is the IR spectra, if you see the spectra, you don't have any idea what kind of things are there. Something is there only, some kind of bands, or you can sometimes call them, there's some kind of peaks. Okay, these kind of things are there. But what basically this constitutes, if you can see it here, is that most important part is that wave number. This side you are having, you know, different wave numbers, 500 to 4000, and here, you know, we have got percentage of transmittance. That means
Pardon,
it is.
sir? Pardon,
Yes.
sir. Sir,
Yes.
slides are not moving actually. We are seeing on the introduction slide only. So it is
Oh.
not going, not changing.
Sure.
Yeah, now it is going, sir.
Now it's going right. Okay.
Yes, sir.
Okay. So it's pretty disgusting actually. Okay. So it is pretty disgusting for me, you know, to see it like this. Okay. Have you seen it now?
Yes,
you
sir.
seen it?
No.
Yeah, yeah. Now you see, you have seen this kind of spectra, and then ideally for, you know, uninitiated, and this bears no meaning. But if you see that here there is wave number as well as percentage of transmittance. Transmittance means after absorption, how much it is. That means how much it is absorbed. If it is not absorbed, how much it is left. When you pass a light through something, how much it is going out of the body, that is the percentage of the transmittance. Suppose if it is absorbed, then it can convert it to different form of energy. So that is different thing. So that means something has got very high transmittance, means it has got very low absorption. That is the idea out here. Okay, so here you can see these are two higher spectra. Actually, this one basically, this one is taken from the bottle. Whatever your, you know, bottle I have shown it, these bottles, whatever I have shown you, from here only we have taken the spectra. This is the IO spectra. But if you see these two spectra, okay, this is for ethanol and this is for isopropanol. Now, as you can see out here, around, you know, 3400 centimeter inverse, something is there, and here also you have got something around 3400 centimeter inverse, and here also like around 3000 you have got some bands. Here also around 3000 some bands are there. So you see that many features are actually almost similar. Here also this area around 1100 you have something. Here also around 1100 something you have. But this side, if you go, this side is, you know, very, very difficult to analyze that which is for what. But this side is pretty clean. Okay. But this side, one interesting feature is there is that for same compound, this particular site will have similar pattern, exactly similar pattern. That's why we call this site as fingerprint region. Okay, fingerprint region. So, but this side you have got very isolated thing where you have got, you know, different frequencies, absorption at different frequencies you will see, and they are very well identifiable. So they are called functional group frequency region, and this is called, you know, fingerprint region, because for same compound, this region you are going to get same thing, no difference at all. So we have got this spectra, one is for isopropanol and one is for ethanol. But idea is that when I have got it, this every single band, I cannot analyze it out here. It is very difficult because in a simple ethanol molecule, as you can see, that you have CC bond, CH bond, OH bond, CO bond, okay? And they will have again different kind of vibrational frequency for each bond, okay? CO will have different vibrational frequency. Even among the CO, you will have CO stretching, CO symmetric stretching, CO asymmetric stretching, CO bending. Within the bending, we have got 4 different type of bendings. So that means you will have a lot of stuff, and most of the bending vibrations are actually, they are found within the region of 1400 and below. Most of the bending vibrations, although some stretching vibrations are also there, but most of the bending vibrations are found out here. And they are pretty difficult otherwise to identify that this bending vibration is exactly for this particular, you know, for this particular bond. So, but here you can very clearly, you can get an idea that what kind of functional groups are there. And I have written this one, as you can see it, that IR cannot be employed as an identification tool for unknown compounds, as it does not give any quantitative information. It is an identification tool, but it is not a complete identification tool. Okay, so to analyze this kind of things, what you will have to do, first you will have to note down the prominent peaks. Now we are talking about not about all the peaks, we are going to talk about only prominent peaks. Suppose here in this molecule, as you can see, this is a prominent peak, this is a prominent peak. Similarly, here some of the prominent peaks are there. So we will first note down the prominent peaks and their frequency, their corresponding absorption frequency. That one we will note it down, and then we'll compare them with the literature data to identify what kind of functional groups are present. Okay, so if you go to this one, this is a typical another IR spectra, where you can see it comes like this. Suppose it is around 2900 something is there, around 1450 something is there. So this is a typical IR spectra which we used to analyze. Now I will tell you that this is what, as you can see, that this IR spectra, you see, this is y-axis, which we have already noted. This is the percentage of transmittance, and here this is the region where electromagnetic field of an oscillating bond interacts with IR light of the same frequency. Okay, where it is transmittance is very low. This is the transmittance. So it is very low. That's why it is coming out here. That means you have in this point very high absorption frequency. Okay, so in this so here also you can see that in this region, you can see up in this region, that means you have very high transmittance. That means there is no absorption practically. Okay, so that is what this is used to identify. So these are different kind of vibrations, as you have found in your spectroscopy syllabus. So we have got stretching vibration, which are symmetric stretching, asymmetric stretching. You can see that both sides it is going in the same direction. So with similar energy, they are stretched. And here this one is coming this side, while this one is going this side. That's why it is asymmetric stretching. And you must have to remember one thing: asymmetric stretching requires always higher energy. That's why asymmetric stretching, their absorption frequency is always higher, okay, than symmetric stretching. Suppose you have got a CH bond, so CH asymmetric stretching will be absorb higher energy than the CH symmetric stretching. So similarly, you have got this kind of bending vibration. Bending vibration. Of course, if you want to pull a bone, pull a spring, suppose, you need more energy. But if you want to bend a spring just temporarily, you don't need that much energy. That's why bending is always energetically lesser than the stretching vibration. So that's why I have shown you that all bending vibration things come around 1400 and below, which is mostly we assigned as fingerprint region. Okay, so here you see it is like a seizure. Okay, so here it is going this direction, it is called rocking. So this is called twisting. Okay, this is in plane, this is out of plane. So out of plane, both are going out, and this is wagging. It is going in the same direction but out of plane. So they are also important. Mostly this gives very significant value in aromatic compound. Okay, that out of plane vibration has got very significant value, which I will discuss later, but they have got very significant value in determining the structure of aromatic compound. Okay, now you see, ideally we have, this is 4 regions of IR spectra are there. Okay, this region, as I have told you, this is the fingerprint region. So here, around 1600 to around 2000, you have got this kind of functional group: C double bond O, C double bond N, C double bond C. Okay, this kind of thing you get it, even N double bond N. Okay, those kind of things you can get it out here. Most of the double bond things you get it in this region 1600 to around 2000. Okay, and this CO basically, as you know, that this you get it, this one you get it around 1700. This C double bond N you get it around 1600. C double bond C, it is just below 1600 and in that range. Okay, then if you go beyond 2000,
Pardon, sir. Pardon, sir. Sir, you have to again unmute your microphone. Someone by mistake touch your muted you.
okay, no problem, no problem.
Sorry, sir.
Yeah, okay. So it is okay, no, right?
Yes, sir. It's all right.
Okay, so now you can see that this region you have got fingerprint region where you have got C single bond C, C single bond N, C single bond O, this kind of thing, C single bond S, then even C halides, those things you get it out here. And this is the double bond region, this is the triple bond region, and this is here you see again single bond region is coming up. Pretty interesting. This single bond region CC, C and CO is coming very down, and this OH, NH, CH, they're coming very up. Why it is so? Ideally, the single bond are not expected to be more stronger than the double bond and triple bond energy, right? But here they are showing that it is very strong. So this is nothing but they are attached with hydrogen, which molecular weight is, you know, as you know, that you have very low weight, only one. So you have got, suppose, you know, if you go to the frequency value out here, you'll see.
Pardon, sir.
Yes.
Sir, participants are getting trouble in seeing the slides. They are saying they are not being able to see the slides.
Have you seen it or not?
I can see, sir, the slide number with the spectra. With slide number 9, we can see. I can see myself slide number 9.
Okay.
After that, the participants are saying they are not seeing.
Is it? Okay. Yeah, have you seen it now?
Yes, we can see. We can see, sir.
Okay. There is some issue. Okay. So now you can see. Yeah. Okay. Now you can see is that by definition, now you have it is visible now. Good.
Sir, we are at slide number 9, sir.
Yeah, that is what. Now?
Still at 9, slide number 9, sir.
You can see it right now also, right?
Yes, slide 10 now it is. We can see slide 10, 9,
Okay.
15.
Okay. So now as you can see out here is that this frequency is dependent upon two important values. One is called, this is K for force constant, and this is the reduced mass. Mu is the reduced mass. So when this reduced mass increases, then definitely this frequency will go down. And if it is, if it is decreases, then definitely frequency will go up. Now, if you see this reduced mass formula is this M1 by M2, M1 M2 is divided by M1 plus M2. Now you see This because it is 1 only. So M1, M2 means 16 plus 16 into 1, that means only 16 divided by 17, right? So that's why this value reduced mass is very low. As a result, they are coming this side. But if you take CC, that means 12 into 12 divided by 12 plus 12, that means you are dividing by 24. Okay, so that entire thing, this is 12 into 12, that means 144, right? So this value is reduced mass is definitely higher. So when it is increasing, so this frequency is decreasing. Although both are single bonds, but here this frequency is decreasing because here reduced mass is increasing. That's why it is, you know, it is high energy. Now you see the spectrum. I have noted down some stretching frequency out here. I hope you have seen this slide. Yeah. So you can see that I have noted down only few. Suppose you know OH, it is 3600 centimeter inverse, N is 3200 centimeter inverse, CH 2900 centimeter inverse. So these are like, you know, above 2000 only we have got OH, NH, CH and C111C. We have only these functional groups, but we'll have to remember these numbers. There is no way out. These numbers you will have to remember. And if you see the spectra here now, you see it is coming at around 3400, which is definitely, it must be OH. OH is there, that is, we are for sure now. And you are getting something which is around 2900, 2800. Okay, so which is, you know, you see that the CH is there. So that means you have got CH things are there, you have got OH things are there. Then you have got other functional groups which I am not going to talk about now. But for this, suppose if you have isopropanol or ethanol, at least you need CH and OH. This stretching has to be there, and both these things are present in your molecule. So with that only, we'll go that to the next one. Right? You are presenting to everyone, sir. Then slide. What is happening?
So we can see slide 11.
Slide you can see, right?
Yes, sir.
Click here to return to. Yeah. But this is pretty interesting. Somehow. Some of these things are not working very good for me. Why it is coming like this? So now if you see that, if you now you can see that you have got this the bone strength, which is also very important, because OH bone length, as you can see out here, OH bone length is the lowest. That's why its absorption is in the higher side. So then NH, then CH. That's why you can see the spectra like that. But from higher, at least you have confirmed that we have OH stretching as well as CH stretching things are there, right? So then we'll go to NMR spectroscopy. From higher, at least we have got that, we have got OH group and CH. Now we'll go to NMR. Now what NMR does is that this is basically the spectra of these two things. One, we are talking that it may be ethanol or it may be isopropanol. Okay. Now, interestingly, both these components, you can see from this color that, one blue color, one red color, just one is black. That means there are three different kind of protons are there. Okay. Here also, if you see blue, red, black. So you have three different kind of protons are there. That means you have three different environment, chemical environment. where you have got the nucleus, NMR nucleus. So here, because for three different kind of protons, you are going to get definitely three signal. So signal is, when you do NMR spectroscopy, this is very important thing, that you first look for how many signals are there. You don't need to think anything else. Just think about, you know, how many signals are there. Now, if you have three signals, that means at least you have three different chemical environment. That is the most important thing. And when you go to, after confirming that number of signals, then you next go to what is the integration. That means how much peak area of each of them. Now this integration thing you can calculate out from here. Suppose it is 1, 2, 3, 3.5. Here it is kind of, you know, 1, 2, 2.5. So this is kind of 1. So you can relate that if it is x, this is twice x, this is kind of thrice x, right? So that means 1:2:3 ratio peaks are there. Now, if you say 1:2:3 ratio, then you must have to realize one thing. In these two molecules, if you see that here 1:2:3, right? CH3 means 3 hydrogen, here 2 hydrogen, here 1 hydrogen. Okay, 1:2:3. But here if you see 1:1:6, that means from integration and signal itself, you are partially sure that it may not be isopropanol, right? For isopropanol, you should have got this integration 6:1:1, but rather you are getting 3:2:1. So from here you have got a tentative idea, maybe you have ethanol in the system, right? So let us confirm it, not stick up down there. So then we go to the chemical safe value. That is the most important thing, because it may have come 1:2:3, but there may be any other compound which may have similarly. Suppose if it is, you just consider Cl, not Cl, maybe some other compound. Suppose NH, Cl, okay, NHCl. So there only one hydrogen will be there. That will be also having a similar thing. But this chemical safe value will tell you the real idea that whether this ethanol is ethanol or not. Now this chemical safe value, basically it is determined. Can I go to next slide? That is better. Yeah. So okay, I have a slide where just to tell you that if you see here, you see you have got three signal. If you see this compound, you have got three signal. Here in this compound you can see 1 color, 2 color, 3 color, 4 color. That means all are different. So you have got 4 signal. Here 1, okay, 2, and this side also 1, 2, same color only, 2 colors are there. That means 2 signal. Here only 1 color having hydrogen, you know, just 1 signal. If you see out here also, it is like that. It is, you know, it is symmetric molecule 1, and here now, you know, degree of symmetry is reducing down. So you can, you know, just cut it out here. Then you can see that it is similar. That means this one and this one 1 signal, this one and this one 1 signal, this one is another signal. That means you are getting 3 signal. Likewise here, this one and this one 1 signal, this one and this one 1 signal. That means 2 signal. Here 1 signal, 2 signal, 3 signal. So here 1 signal, 2 signals. So this can, that way we can calculate that how many signals you can have in a molecule. Now this is typical NMR spectrometer, which I'm not going to talk now because already we have taken time. Okay, now you see this is the important thing. I will not talk about theory now because you see this is simple methanol structure. Okay, so methanol, you have got CH3. Okay, this CH3, these 3 hydrogen, you know, they used to come upfield. While this one, this oxygen is attached to this hydrogen, as you can see, because oxygen will have, it is, you know, highly electronegative, so it will pull down electron toward itself, thereby making this nucleus, hydrogen nucleus, exposed to the external magnetic field. Okay, when it's exposed to the external magnetic field, then it will be aligned more easily. So as a result, it will be absorbed at a lower energy than this one. because here it is not pulling much, because it is attached to carbon, but here it is attached to oxygen. That's why these electrons are pulled out here. So that's why it is make it naked, but here it is electron clouds are still there around. So it is absorbed upfill while it is downfill. So if you see the NMR spectra, that means it will come little downfill while other one will come upfill. And this is controlled by, as you have seen, that electronegativity of the attached atoms. Okay. So chemical shift is resonance frequency of a nucleus with respect to tetramethylsilane. So it is whatever downfill, upfill we are talking about. There is a molecule called tetramethylsilane, where it is taken as it is absorbed at 0 ppm. So with 0 ppm, how much change is there? That is only noted in NMR spectroscopy. Now these are the three factors which are most important, which affect the chemical shift. That is electronegativity, which I have already discussed. There is another called anisotropy, the compound having double bond and triple bonds. Suppose aromatic compounds, alkenes, alkynes, they have got an effect which is called anisotropy. Suppose you can consider a double bond, suppose ethane. It's a molecule, that means your double bond means this molecule is planar in structure. Structure is planar. Suppose you see it out here, it is a planar structure. When you have a planar structure, that means your electron cloud will be on the plane. So when there is a moving electron cloud will be there, as you know, this moving electron cloud will generate a magnetic field, magnetic lines of force, which is perpendicular to it. So that's why you see out here, as electrons are moving this direction, that means, but this is horizontally. That's why perpendicularly you are having a magnetic lines of force. And this magnetic lines of force, as you can see out here, that it is going up, this is going up, this is going up, and this is the applied magnetic field direction. That means it is aligned to the applied magnetic field direction. That's why that means it is easily, these kind of protons can be easily aligned to the applied magnetic field. But here in this case, you see this is alkyne, where you have got a ring, because triple bond, it's a triple bond. So triple bonds are basically kind of like a cylinder. So an electron will be moving in the periphery of the cylinder. So when electrons are moving on the periphery of the cylinder, perpendicular to it, there will be magnetic lines of force like this. Okay, so it will basically it will try to oppose it. When it opposes the applied magnetic field, then you can see this side it is increasing, but this side it is basically decreasing, because it is opposing out here and out here. So that's why here this value is little bit uphill than simple alkenes. Now I have given you this one, that this saturated CH will come out here around 2 and below. Then it is allylic compounds. Then you have CH2X halogen, then CH2O, CH2N. These things comes at 2.5 to around 4.5. Okay. Then you have got vinylic, which is around 5. All double bond thing, they comes after 5. That means after 5 to 10. Okay. So if there is no electron withdrawing group, then it will be nearer to 5. If it is electron withdrawing group, then it will come even further down to 10 ppm, 9 ppm, 8 ppm, like that. An aromatic compound, because it has got electron ring. So as a result of that, it produces even a higher magnetic field, which higher induced magnetic field, which can be aligned with the applied magnetic field. That's why they used to come even further down. So aromatic compounds, basically they used to come, you can say that around 7. Okay, simple double bond, it comes around 5. So if you have this kind of compound attached to nitrogen, oxygen, then you can get it around 3 to 4.5. So this is aldehyde, this is acid. So that way only few numbers you need to remember to get the idea. Now let's go to our molecule. Now in this molecule, as I have seen, that as you have seen the earlier one, that we are telling anything less than 2 may be CH, saturated. So that means here it must be something saturated thing is there. That means these 3 protons, whatever it is there, it must be away from the electronegative oxygen, right? Then because this CH2 are attached with oxygen, so that's why it will be, you know, definitely pulling up the electron. So that's why they are more deshielded, and they are coming around 3.7. Okay, so then you have got, this is always peak because oxygen is attached directly with hydrogen, so this hydrogen is even coming down. That means you are getting a thing that where you have got saturated CH, then CH attached with oxygen, as we have seen from the earlier chart, and then you have got hydrogen directly attached with oxygen. Sometimes this hydrogen, sometimes it does not come as well. So now question is that, what is these lines? Each signal you have got 3 lines, this is 4 lines, this is 1 line. Why it is so? Now this is what is called multiplicity. Multiplicity is determined by, this is very important in NMR spectroscopy. Multiplicity is determined by the number of neighboring protons. That is very important. That means you can predict your neighbor. Suppose a particular proton is there, what kind of neighbor is there, that you can judge is by seeing the multiplicity of that particular bit. So here it is signal, because it is coming a triplet, so we know that there must be 2 neighboring protons. Okay, so let's go to next slide. Okay, now you can see how multiplicity thing actually comes up. Now suppose you have 2, we can take this, you know, protons HA and HB, we can just take them as a 2 isolated magnet, small bar magnet. Okay, this is the magnet. So magnets, as you know, if you bring it together nearer, they have either attraction force or they have repulsion force. Suppose if you want to attach, bring south near south, then definitely they will repel, right? But if you do otherwise, north to south, they will attract. So this attraction thing is rather easier, and repulsion needs even higher energy, right? Repulsion always needs kind of high energy. So that means if you have 2 this kind of bar magnet, 2 bar magnet, then they may either arrange it like this. Okay, they may either arrange it like this, or they may arrange it, you see, north south, both similar spin is similar. Then here north south, but north south opposite, so you have opposite spin, right? So that means if you have 2 neighboring, if you have, suppose this is the proton, if you have 1 neighboring proton, that means you are going to get definitely 2 different energy level. So 2 different energy level means you are going to get 2 peaks in a signal. That is what is shown out here. Okay, so that is the applied magnetic field. As I can see, this is the applied magnetic field. So this proton can be up or it can be down. If it is only 1 neighboring proton, it can be up or it can be down. Or if you have 2 neighboring proton, both can be up, 1 can be up, 1 can be down, both can be down. So that way, if you see it, that if you have only, you know, 1 neighboring proton, you will get 2 peaks. If you have 2 neighboring proton, you have got 1, 2, 3 peaks in a signal. If you have 3 neighboring proton, you are going to get 1, 2, 3, 4, right? So that means here it is 5. So that means if the number is that if you have neighboring proton 1, then you are getting 2 peaks. That means you have n plus 1 rule is there. Okay, so that means neighboring proton can be determined by the number of splitting. Okay, so you will see that it is like a Pascal type thing is going up. Okay, Pascal type thing is going up. It's a singlet, it's a doublet, it's a triplet, it's a quadruplet, it's a quintet, sextet. So these are showing the intensity. Actually, these numbers are showing the intensity, that which peak will be higher. So this entire phenomena is called spin-spin coupling. Spin-spin coupling, and spin-spin coupling is why so important, because it gives you the idea about neighboring protons. That is very important. How many neighboring protons are there? So here, as you can see out here, is that this is, you know, this is side X, this side X, hydrogens are there. So you will have first only, suppose for this proton you have only 1 neighboring proton is there. So it will be breaking like this, right? So if you have another neighboring proton, I should have written another neighboring proton, then you should have been triplet. In this case, actually, in ethanol, as you know, you have got CH2 in the molecule. So if it, now there is another thing. Suppose if you have one is X attached to X, one is attached to Y, okay, then sometimes it changes. Their coupling energy is different, okay. It is, you see, this is E1, this energy is E2, because both hydrogens are coupled with two different kind of nucleus, okay. This hydrogen, it is attached with X, this hydrogen, it is attached with something Y, so they will be different. These are actually two ethanol spectra only. This is the ethanol spectra where moisture is there actually. As a result of that, you are getting the spectra. And here it is ultra pure ethanol, and where it is, you see, it is a triplet, but it is not triplet. Actually, it is called quartet of doublet. Okay, quartet of doublet, and it is also not singlet. It's a triplet. How it is so? I will show you the, okay, how it is so, because that I think I did not explain it. Okay, if you see in this molecule out here, suppose CH3, you have got, you know, CH2. Two neighboring proton means this CH3 will give a triplet, right? And this CH2, these two hydrogen, it is attached with one neighboring proton this side, three neighboring proton this side. So that means you have got four neighboring proton. So it should give minimum a pentate. Okay, minimum a pentate. But in our case, we did not get a pentate. In our case, we got a just a quartet. Why you got the quartet? Because this OH, which is oxygen attached with water. So if any oxygen attached with hydrogen, if any moisture is there, then this water will exchange with the moisture in the solvent. When this exchange means its position is not fixed. When this position is not fixed, that means it cannot interact with this hydrogen on a regular basis. That's why we are not getting any interaction due to this, and this is coming as a singlet. That's why you are getting always as a singlet, while this one you are getting a quartet, because there are three neighboring hydrogens. 3 plus 1 means 4, and for this one you are getting a triplet, which is because there is two neighboring protons are there, right? So here that is why you are getting this picture, which is like this. That's it's a triplet, it's a quartet, it's a singlet, because this oxygen attached, a hydrogen attached with oxygen is actually not staying together in the molecule. It is exchanging with moisture in the solvent. That's why it is coming as a singlet. It is not interacting with neighboring hydrogen. But in this case, when it is ultra pure, there is no other thing, then it is not exchanging. So when it is not exchanging, they will have definitely this kind of spectra where you have got coupling constant difference also, because one hydrogen is attached with oxygen, while other hydrogen is attached with carbon. So that's why their coupling constant difference is there. That's why you used to get for this kind of compound that difference splitting pattern. So you see isopropanol, this is isopropanol, where as you can see that this is 6, this is 1, this is 1, because our compound we could not find this one because our spectra was completely different. So from there we can say that at least we did not have any isopropanol in the system, right? Let's go to mass spectroscopy. So that's, you know, this is another important thing where what we used to do basically, as you can see out here, that suppose this is a jar. Mass spectroscopy, what they used to do is that this jar is attacked by electron, and then you are breaking the jar and you are analyzing individual component to find out what is the molecule is. So that is the formula. Here, as I have shown here out here, you are attacking with an electron, that okay, electron beam. When electron beam you are attacking, it is generating M positive charge and 2 electrons are gone away. So, and this one, when it is M positive, it depends upon the stability. This is called molecular ion pair. And it depends upon stability. If it is not stable, then it will break down further. Then it can give you a daughter ion, that means D plus, or daughter ion radical, and along with neutral molecule or radical it can give. So that is what mass spectroscopy basically is. That means what we do is that a compound is treated with an electron beam. Okay, so when you are treating with electron beam, it takes out one electron from the surface of the surface of the molecule, thereby generating a positive charge. It may take out even 2 electron, 3 electron also, but ideally most of the things they used to give M+. Okay, then if M+ is not stable, then that will break further to further data this kind of daughter ion, that means D+ or D+ radical, and neutral molecule or radical it can do. Now for your sanitizer, what happened is that we got a mass spectra which is like this. Now if you see this out here, that you see this mass is 40, 42, 44, 46. Mass is 46. Now if mass is 46, it fits very nicely into ethanol, and ethanol has also molecular mass is 46. So it exactly says that this is, we call it molecular ion peak. Okay, this is the molecular ion peak, and this one gives an idea that you have this you have this compound. Then after that it breaks down. Suppose you are getting another at 45, you are getting something at 33, you are getting something at 31, then 29, then 28. All this peak will analyze to see that whether it is ethanol or not. Okay, let's go to see this one now. Now, as I have told you, this is the molecular ion peak. This is the molecular ion peak. Okay, so which is M is equal to 46. M by Z. It is expressed in M by Z. M is the molecular mass, Z is the charge, because if it is M2 plus, then it will be divided by 2. So Z is very important. So M by Z is 46. That's why it is coming at 46, right? So when you treat this one with electron, where electron is available out here? Because here in oxygen you have non-bonding electron. When you have this non-bonding electron pair, so these electrons are easier to remove. So that's why one electron is removed from here to make a radical cation like this, right? When this radical cation is done, then what it will do is that it will take, you see, this radical, and it can break this bond. It can break this bond to make it something like this. Okay, this cation, which is 45, that means one radical is moved out, which I have shown earlier also, that you can eliminate a radical. So you have got a positive charge which is 45, which is I am showing out here. Now it can, you see, this bond, this CH bond is attached with this carbon. So this carbon, there is another carbon bond. This bond can also break. Ideally, this bond should break more because it is heavier. Any heavier bond breaks faster. So if you break this bond, then what will happen? Then one CH3 radical will go out. Then you are getting something which is 31. Here you see, this is the 31. Okay, this is 31, which is the most stable peak in this mass spectra. So which is called base peak. Base peak is considered as 100%, and all other peaks are just intensity of other peaks are considered with respect to the base peak. So base peak is not basically molecular ion peak. It can be sometimes molecular ion peak, but base peak is the peak which has got the highest intensity in a mass spectrum, right? So I'm almost finishing it. So now you can have it other way around, that it can be, if you break it like this, it can be like this also. Okay, if you break it this way, then you have got CH3 plus. Here we are removing as a radical, but here we are removing as a positive charge. So M15 is there. So M15 peak also you will get in the spectra. Of course, it is not very prominent out here, but you can get this OH also, you can remove it this way. Then you can get CH3, CH2 plus, which is 29, which is also out here, 29. Okay, so that way we can analyze, and from each component, when we get it that, okay, you have got 29 peak, 45 peak, 46 peak, okay, 15 feet. So we are more or less sure that this is possible only if this molecule is ethanol. It is not isopropanol. So there is a particular pattern in mass spectroscopy breaking. So how this, when you treat with electron, then ideally electron goes from non-bonding very fast. If non-bonding electron is not there, then it will go from this pi bonding. Then if it is not going from there, then it will go from sigma bonding. Then you have beta cleavage, which is more preferred than alpha cleavage. Then if you have larger group, as I have shown out here, if you have larger group, that will break as a radical because it will make the molecule smaller and that will make more stable thing. So from all this data, so we have found out that basically it is a Dettol, okay, instant hand sanitizer having ethanol in it, okay. So I think I just tried to convey something because this presentation has some issues. That's why I could not get it. Maybe I don't know how much I could get you, but this is the way that you can identify or characterize the compounds of a sample. So with this, I will thank you everyone, and I will expect that questions from your side if you have any. Okay.
Thank you, Professor Bess, for your inspiring and valuable lecture and your nice presentation. Hope our students will be much more benefited from this lecture. Thank you again. At the very beginning, I asked students to put question in the chat box, but there are many more questions in the chat box. It is not possible to see the questions. So I asked students directly to direct your person if any questions you have, and I request or assistant coordinator Dr. Sampok Doctor to conduct the questionnaire session. Sampok, please.
Yes. Thank you, ma'am. Professor Bess, first question we have for you is from Pranjit Kumar Bara. He is asking, do NMR solvents affect the chemical shapes?
Yes, yeah.
Pranjit Kumar Bara wants to know if the NMR solvents affect the chemical shape in a spectra or not.
Yes. That is what I have already explained in ethanol example. That if you have slight amount of a solvent is there, if there is a slight amount of even moisture is also part of a solvent. So then you have got completely different spectra altogether. And second thing is that some of the solvents, suppose benzene. Okay, benzene, you have got, it behaves like it itself behaves like a magnet. You take an NMR spectra in simple CDCl tree, and you take the spectra in benzene. You will see that in benzene there will be downfield shift of all the signals in the molecule. Why? Because benzene itself behaves as a magnetic field inside the system. So solvent is huge role, and that's why always in NMR spectroscopy, when you write it, you know that the solvent is very important. Yes. Yes.
Thank you, sir. We cannot see any more questions. Participants, I request you to put questions. Okay, second question we have got here from Priya Gogoy. Why mass spectrometry is not spectroscopy? I think she wants to know the difference between spectroscopy and spectrometry.
Okay. I'm kind of feeling it that because this is MSc Viva, we used to ask students that why mass spectroscopy is not spectrometry. I think the student knows the answer. Okay, because spectroscopy means is that interaction of radiation with light. Okay. So here actually no radiation is involved. So it is not, that's why it is not called spectroscopy. Rather it is called a spectrometry. Because it is ionization sources used. Ionization source, that means electron bombardment. So practically you are not using any light. That's why it is spectrometry, because it gives like a simple spectroscopic the data. So that's why it is called spectrometry, not spectroscopy. Yeah. Please, any more question? Actually, another question I am getting, how 500 megahertz is different from 400 megahertz instrument. Now, important thing is that this instruments, why we are not dealing with 60 megahertz instrument, we are going for 500 megahertz instrument. Because in 500 megahertz instrument, we are dealing with higher applied magnetic field. And when you have got higher applied magnetic field, means you have got different, much higher magnetic moment, right? So that magnetic moment will separate between two energy levels. So energy levels are always expands. So as a result, you get a better spectra. That means resolution becomes better. Okay. Suppose, for example, in a 400 megahertz NMR, I will not take 400 of a little leisure. Suppose 200 megahertz NMR. 200 megahertz NMR, 1 ppm means 200 hertz, right? And 500 megahertz NMR, 1 ppm means 500 hertz. So that means your difference between the peaks in the signal will be much clear. That means you are going to get better resolution out there. Yes, next question. Any more question? I'll appreciate it definitely.
We cannot see any more questions. We will wait to see 1 or 2 minutes.
Yeah, because talking about IR, NMR, and mass in a 1 hour lecture is actually really unthinkable. Somehow I thought that, okay, can I tell at least something that where student can get something out of it? Yes, please. Any more question, students?
So Pranjit Kumar Bora is asking about he's asking to speak to you about GCMS briefly.
Yeah. This GCMS also, actually it is kind of GCMS means you have got GC, that means gas chromatography component, and you have got mass component. Mass, whatever I have discussed, it is same thing. Only thing is that just chromatography is involved there. So what it is done is that in GC, compound is injected to a oven which temperature may be around 300 degrees. So they will make vapor of the compound, then it will pass through a column. Column is in this case actually just wire, where you have got, it is loaded with stationary phase. So this stationary phase will decide that, okay, how much this gas is passing through that simple stationary phase, and how much their speed. Okay, that will depend their RF. Basically, you can say simple TLC form. So their RF will decide that, okay, which one is going faster to the mass detector. So in the mass detector, it will break it similar way what we have discussed now. So there is no difference. That means just one chromatography part is there. It is gas chromatograph, and other part is simple mass. So compound will get purified in the GC, and then will enter the mass system. And in the mass, it will be broken first, then it will be recorded.
As we are running short of time, so we'll take the last question. So Iftikhar Hussain is asking to talk about Raman spectroscopy.
Raman spectroscopy, because okay, Raman spectroscopy is like simple IR spectroscopy. Only thing is that, suppose simple carbon dioxide, if you can think. Carbon dioxide, if you go for symmetric stretching, then problem is that there is no difference in magnetic moment. Okay, there is no difference in their polarity, right? So in that case, in IR spectroscopy, those compounds getting identifying this kind of compounds are difficult. So what Raman spectroscopy used to do is that they used to put an additional magnetic field. Because of the presence of this magnetic field, they are now just polarized. Okay, so that then you can detect this compound very easily. So it is as simple as that. Yes.
Thank you very much, sir. So here we are wrapping up the questionnaire session. Now I'd like to request our HOD ma'am to carry on the forum. Ma'am, your cue.
Thank you again, Professor Bess, for your nice presentation. I hope our student must be benefited from this lecture. Thank you again. Now we are at the end of our discussion. I also request our participant to fill up the feedback form, which was already sent to you in your emails. And after getting your feedback form, I'll send a certificate to you via email. Now, I would like to request our Assistant Coordinator, Ms. Arhana Soikia, to give the vote of thanks. Please, Arhana.
Yes. Thank you, ma'am. Respected principal sir, distinguished guests, colleagues, and participants. First of all, I'd like to propose my sincere vote of thanks to our principal sir for inaugurating the webinar and offering his all administrative support to conduct this webinar. I'd like to offer my sincere vote of thanks to our distinguished resource persons, Dr. Ghanshyam Bes sir and Dr. Ramesh Chandra Dekar sir, who spend their valuable time and make our webinar a successful one by delivering valuable lecture on two most important topics. In successful conduct of this webinar, the technical work was done by Mr. Jayanta Bardoloi sir, Assistant Professor, Department of Computer Science. I would like to offer my sincere vote of thanks to Mr. Bardoloi sir. My sincere thanks goes to Dr. Pankaj Kara, Dr. Sangeeta Das, and Konkana for their valuable support in conducting this webinar. Though it is a part of the organizer, it is worthwhile to offer my sincere thanks to Dr. Parinita Bora ma'am, head of the Department of Chemistry, for her inspiration and valuable discussion throughout the webinar. My sincere thanks also goes to Dr. Sampak Datta for his valuable support. Last but surely not least, I would like to offer my sincere thanks to all the participants for valuable presence of the webinar. Once again, I thank you all for being with us. Thank you.
Thank you, Arhana. Now the webinar is concluded. Thank you all. Thank you.
Thank you. Thank you.
Thank you. Yes, thank you.